So we're just going to pick up from where we left off last day. We were talking about lists. In the previous lecture, we did a little simulation for estimating the odds of rolling a pair of dice. Today, it's something similar. Well, very quickly, I'm just going to do another quick simulation, this time for flipping coins. And so I want to look at the question where if you flip a coin n times, how many times do you expect to see m heads, for example? And so we can solve the problem in a similar way. Right? We make a list and populate the, so if we're flipping the coin n times, we're going to make a list with n plus 1 elements in it. Right? Index 0, that's the number of times you see 0 heads, so that should be probability 0. No, there should be some small probability here. Right? And index n, that's going to be the number of times you see n heads. Right? So we're going to make a little list, we're going to populate it with a bunch of zeros, then we're going to start flipping coins n times. And we're going to do that many times. Right? After you flip the coin n times, you're going to count how many heads you saw. Then you're going to go into the list. So if I saw 2 heads, I'll go into the list, look at that number there, which should be 0, and then add 1 to it. Right? So we're just going to count the number of times we see n heads. Right? And so that's the little algorithm that you can use there to solve the problem. Right? You make a list, add n plus 1 zeros to it, and then you write a little loop. Runs m times. Right. Inside the loop, you set the count to 0. So that's the count is the number of heads you see for this trial, right? And you're going to run m trials. Right. Now you flip your coin n times, count the number of heads, store the number of heads in our table, right? And then if you want to, you can divide the elements in the list by m to get the actual odds. Right. There's the code for it. So it's pretty similar to the previous lecture, right? We're going to, for this simulation, we're going to flip the coin 20 times. We're going to do it 1,000,000 times. Right? So there's my list of probabilities. Right? I'm going to put n plus 1 elements into the list. Right? So I'm going to put n plus 1 zeros in that list. I'm going to make a little random number generator right there. Right? And then I'm going to repeat the coin flipping experiment m times, right? Where m is 1,000,000 in this case. Right? So each time for each trial, we're just going to count how many heads we see when we flip the coin n times. Right? So there's the flipping of the coin n times. Right? Now to simulate flipping a coin, you just need a random value that's true or false. So we can use next Boolean to get a random true-false value. Right? If we see true, we're just going to assume it's a head. Otherwise, it's a tail. Right? So every time we see a head, we're going to add 1 to the count. And then you're going to go into your table, right, and get the current count. And add 1 to it, and then put it back into the table, right, using set. So use get to get the current count, use set to set the current count. Right? And then at the end, we can divide all of the counts by by m, and that gives you your table of probabilities. Right? So you can run that, you can just copy that slide into Eclipse and run it and see what you get. It does actually work, and you do get an approximation to the binomial distribution. All right, I'm pretty sure you've seen recursion before, right? A little bit? Okay, so if you want to solve a problem with recursion, there has to be, there's a condition on the types of problems that you can solve with recursion. Right? So when you use recursion, right, you have a function or a method that calls itself. Right? But when it calls itself, it has to be calling itself to solve a smaller version of the problem than it's currently trying to solve. Right? So that is, recursion tries to drive the problem size down towards a base case. Right? When you hit a base case, you find your answer, and then you can unwind the recursion. Right? But one of the hallmarks is it has to it's trying to solve a smaller version of the problem each time it calls itself. So lists, you can think of a list. So for recursions on lists, right? If I'm trying to solve a problem on a list and I want to use recursion, then it has to be the case that every time I recursively call the method, I'm calling it with a smaller version of the list. And so I'm going to give you 2 examples of problems that you might solve using recursion with lists. So we've got this little game. It's not the most exciting game in the world. It's called Jump It. It's made up of a list or an array. Right? So it has n squares. N has to be greater than or equal to 2. You're always starting at the left-hand square. Right? And you're trying to get to the right-hand square. So the rules of the game are, starting at the left-hand square, you can move 1 or 2 spaces at each step. Right? Every time you land on a square, the square indicates the cost of stepping on that square. Right? So here we start with a cost of 0. If I take 1 step, I now have 0 plus 3. Right? So total cost of 3. If I make another step, I now have plus 80, so 83, and so on and so on and so on. So the goal is to make it to the end of the board with the minimum cost. Right? Your costs are always positive here. Okay, so what is the minimum solution? What is the minimum cost solution for this board? So go to the 3, right? Then go to the 6, and then go to the 10, right? And your total cost is 0 plus 3 plus 6 plus 10. Right? So if you look at the solution, so first of all, this solution, the board is small enough that you can just eyeball the solution. If you try to formalize what we did, you might say that, well, starting at the 0, I can go to the 3 or the 80, so I'm going to choose the 3. Right? I'm always going to choose the smallest. I'm going to choose the move with the smallest cost. Right? Now, starting at the 3, I can go to the 80 or the 6, so the 6 is smaller, so I'll go to the 6. Right? And at the 6, I can go to the 57 or the 10, so I'm just going to go to the 10. Right? And so that would be a greedy solution to the problem, which you can code up using a little for loop or a little while loop. Right? So always take the step. Always take the next step that has the smallest cost. Right? So the question is can you solve this particular problem in this way? Right? So greedy solutions often work. Does it work here? The answer is no. Right? It doesn't work here. So the reason it doesn't work here is because you might end up, it might be better to move to a square with a higher cost because you would have ended up on that square anyway, regardless of what you did. Right? So for example, if I use the greedy solution and I'm on the 17, right, my choice is between the 1 or the 5, so I move to the 1. Right? Now my choice is between the 5 or the 6, so I move to the 5. Right? And now my choice is between the 6 or the 1, so I move to the 1. Right? But there's actually a lower cost solution. Right? You can actually skip stepping on the 1 if you just jump straight to the 5. Right? And so there is actually a solution here where the greedy solution, this is a case where the greedy solution fails to find the lowest cost solution. So the problem with this, so in this problem, the one way to solve it is to try every possible move. Right? So at your first step, you'll try to take both moves, right? So 1 square and then 2 squares, and then see what happens, right? And then so on and so on and so on. If you try to write your solution that way using a loop, you'll find very quickly that it's not so easy to do unless you know a trick, right? So instead, let's attempt a recursive solution, right? Why can we attempt a recursive solution here? Because every time we take a step, the board gets smaller, right? I can ignore everything to the left of the current square, right? So when I move right 1 square, the board gets smaller by 1. If I move right 2 squares, the board gets smaller by 2. So there could be a recursive solution in this case. Now, if you're going to formulate a recursive solution, you need your base cases. Right? So those are the cases where you know the answer to the problem you're trying to solve. And you need your recursive cases. Right? So those are your recursive calls to your method where you're solving a smaller version of the same problem. Right? And so always in these types of problems, it's useful to draw a sketch of what's happening. Right? Normally, it helps you find the base cases, and it might help you find the recursive cases. Right? So for this problem, we can just go back to, say, this sketch over here. Right? And imagine that we had a board of size 2, right? Because that's the smallest size board. Right? So if I have a board of size 2, you know the answer. Right? Your total cost is the cost of the current square and the cost of the next square. Right? So that's easy. What if I have a board of size 3? Right? So 5, 6, and 1 in this case. So you also know the answer if the board size reaches 3, right? You just ignore the second square and jump straight to the last square, right? If your board size is 4, this is where you might have to make a decision, right? Maybe I move to the first square, maybe I move to the second square, but I don't know which one to move to, right? And so your base cases in this case are if the board size is 2, right? So you have no choice of your move. You have to move to that last square. Right? Or your board size is 3, in which case I'm always going to move 2 squares because I'm going to avoid the middle square. right? And in both of those cases, it's trivial to evaluate the cost. All right, what about the recursive cases? Oh, so there's here, so I'm going to implement a method called cost. It's going to be recursive. It's going to return the total cost of solving that board, right? So the total cost of solving that board. So here's my base cases, right? For the case where the size of the board is 2 and where it's 3. Now what about the recursive cases? Right? So if I'm not in either one of these cases, I have to do something else, right? So now there's a decision to be made, right? So the decision in this case is, well, I have to try moving one square, right? And then I have to compute the cost of the rest of the board, right? The other case is I'm going to move 2 squares, right? And then I have to compute the cost of the rest of the board, right? So I'm going to compute 2 separate costs, right? And then I'm going to look at which one's smaller, right? Whichever one's smaller produces the minimum cost solution. Okay. So how do I find the cost after moving 1 square, right? Well, the cost method computes the cost of solving some board. So if I can compute the board that's missing the first square, I can just recursively call cost. Right? Similarly, how do I compute the cost of moving 2 squares? Right? Well, the cost method computes the cost of solving some board. Right? So if I can compute the board missing the first 2 squares, I can just call the cost method. Right? And it's easy to compute the board missing its first and second square. Right? There's a sublist method in list. Right? So sublist 1, comma board size, returns the part of the list not including the first element in the list. Right? So starting at index 1, going up to the end of the board. Right? It gives you back that part of the list. So that was easy. Right? What about taking 2 steps? Well, I can use sublist again. Right? And I can get the part of the board starting at index 2. Right? So in other words, missing the first 2 elements of the list. Right? Going up to the end of the list. Right? Now I can compute the cost of moving 1 step and 2 steps. Right? So the cost of moving 1 step is the cost of the current square, which I'm on, right? Plus the cost after moving 1 step. Right? So just recursively call cost and pass it in the smaller board. Right? What about the cost of moving 2 steps? Well, it's still the cost of the current square plus, right, the cost after moving 2 steps. Right? So just call cost and pass in the board missing the first 2 squares. Right? So recursion will take care of computing that cost, right? And recursion will take care of computing that cost, right? At which point you know you can pick the smaller of the 2 costs, right? Which I can compute using min. So math.min computes the min of 2 values, right? And you add that to the cost of the current square and you're done, right? And you've got a very small, a very compact solution to the problem. Right? If you tried to solve this using a loop or loops, you'll quickly realize that it's much harder to solve the problem iteratively. Right? But the recursive solution is small and elegant if you like recursion. If you don't like recursion, it sucks, but that's life. Right? Okay, so we can get the smallest cost, but can you actually get the sequence of moves? Right? So can you modify cost so that it also produces a list of moves? Right? So for this board here, I take 1 step, 2 steps, 2 steps. Right? So I would like to get the list 1, 2, 2, as well as the smallest cost. Right? So how do you do that? So I suggest you can use the following method right there. You can use that method signature right there. Right? So you're still going to pass in the board, but now you're also going to pass in the list of moves. Right? So when you call the method the first time, you're going to pass it in an empty list. Right? Every time the method makes a move, it's going to add that move to the list somehow. Right? So the method now modifies the incoming list moves. Right? It never modifies the incoming board. Right? So there's nothing in the method here that changes the actual board. Right? There's no set, there's no set, remove, or add in this method. Right? So the board never changes, which is nice. Right? You shouldn't change the caller's board to compute the cost. So I'm not going to show you the answer to this. I'm going to leave that as an exercise for the student. All right, so that particular problem has a couple of nice properties. Right? So number one, it's clear that after every step, the board's getting smaller. Right? And so that naturally leads you to recursion. The other property of this game is that it's impossible to move to the same square twice. Right? And it's impossible to move off the end of the board. Right? So there's no way you can fall off the board on either end. Right? So I don't care about dealing with the indexes at all. Right? But you can easily remove those three properties to produce a harder version of the problem. Right? So again, it's a similar type of game. I'm going to start at the left-hand side. Right? The numbers in the list, they're all positive except the last one. Right? So the last square is always 0. The goal is to move from the left-hand side of the square, board to the right-hand side of the board. Now, when you move to the number in the square, tells you the number of squares that you can move, left or right. Right? So starting at the 2, and you're never allowed to fall off the board. So starting at the 2, I can move 2 squares left or right, but I can't move left because there's no squares to the left. So I can move to the 4. Right? Going to the 4, I'm allowed to move 4 squares left or right, but I can't move left because I'd fall off the board, so I have to move to the 1. Right? Now the 1, I can go to the 2 or the 6, and so on and so on and so on. Right? And so the question is there a solution to this particular board? Right? So it turns out there's more than one solution for this board. Right? So starting at the 2, I can move 2 squares to the right, can't move left. Right? Then I go to the 4. Right? From the 4, I can only move to the right. Right? Now I'm at the 1, I can move to the 2 or the 6. So let's go to the 6. Right? From the 6, I can't move right because I'd fall off the board, so I have to go left. Right? Now from the 3, I can't go left, so I have to go right. When I get to the 5, I now have a jump to the end of the board. Right? So there is a solution. There's another solution. Right? So go to the 4, go to the 1. Now instead of going to the 6, I'm going to go to the 2. Right? And when I go to the 2, I can go to the 6, which would lead me to a solution. Right? Or I can go to the 2. Right? And notice there's something funny about this 2. Right? If I land on that 2, I'm allowed to go back to the other 2. But that doesn't actually help me get to a solution. Right? It just sends me in a circle. Right? So instead, I'm going to go to the 3. And now I can go to the 5, and then I go to the 0. Right? So there are multiple solutions on this particular board. Right? In this game, it's possible that you end up on that you land on a square, which can take you back to a previously visited square. Right? So that's what we call a cycle. Right? So here we've got a cycle of length 1. Right? The 2 goes to the 2, goes back to the 2. Right? You can have cycles of longer length. Right? So you can go to the 2 and then to another square and then come back to the starting 2. Right? And so on and so on. So you want to avoid, in your solution, you want to avoid falling into a cycle. Right? And using cycles, you can easily make a board where no solution exists. Right? So this board, there's no possible solution. Right? You just keep on going around in a circle. Right? And on this board here, if you try it out, no matter what happens, you end up on the 1, which puts you into another cycle. Right? You end up in a cycle here because you started at the 2. Right? From that 2, you have to move to that 2. So after one move, you've been to both 2s. If you end up on the 1, you again end up on one of those 2 2s. Right? So on this board, no matter what, you end up in a cycle. And you don't need cycles to create a board that has no solution. Right? This board here has no solution because as soon as you land on the 100, you can't go left or right. All right, so if you try to solve this problem, again, if you try to solve it iteratively, you'll quickly realize that there's no simple way to solve the problem. Right? So you might say, well, why don't we try a recursive solution? Right? And then you remember, well, in the recursive solution, the board has to get smaller. Right? But it doesn't really, at first glance, it doesn't look like the board gets smaller here. Right? So if I move to the 2, right, that doesn't necessarily rule out that 2. Right? Because I can come back to that 2. Right? But then you think, oh, I want to avoid cycles, and then you say, oh yeah, so the board does get smaller. Right? If I've been on the 2, right, I never want to come back to that 2. So the board does in fact get smaller every time. Right? I just have to remember which squares have I stepped on as I try to solve the problem. Right? So the board does get smaller. I need some way to indicate that I've landed on a square before. Right? There's lots of ways to indicate that you've been on a square before. All right, so let's try a recursive solution for this. So instead of starting at the base cases, I'm going to start at the recursive cases, right? Just because I can, right? There's no good reason why I'm starting with the recursive cases. Okay, so your recursive cases are, well, I have to try solving the board moving left or right, right? So can you move left without falling off the board, right? If the answer is yes, right, then you want to ask the question, can I solve the board by moving left? Right? Similarly, your second choice is, can you move right without falling off the board? Right? If you can, you want to ask the question, can we solve the board by moving to the right? Right? So we're going to write the following method, is solvable, right? It returns true or false, depending on whether or not the board is solvable, right? You're going to start at this index here, right? So that's the current index that where you are on the board, right? And that's your board. Notice here that the method does not permanently modify the board, right? So if someone calls the method with their list, when the method returns, their list appears to the caller to be unchanged, right? So we are allowed to change the board inside the method, but whatever we do to the board, we have to change it back to its original state. Right? So this method here, I claim, will solve any board if you're currently on that index. Right? All right, so our base cases are going to go up here, but we haven't done them yet. Right? So I'm going to do the recursive cases first. Right? All right, so I'm on a square. Right? We're on the square given by index. Sorry. Right? So I need to know how many squares can I move. Right? So that's going to be value. So I have to get the value of the board at the given index. Right? So I'm currently on that square. I need some way to indicate that I should not come back to the square again. So I'm going to temporarily set the board location to -1. Right? So negative numbers are illegal in this game. So I can use -1 to indicate that I've stepped on the square before. Right? I just have to remember that I have to put it back before I return from the method. Okay, so can we move by going left? Right? So if I move left, right, then the square that you land on has index, the current index, right, minus the number of squares that you move. Right? So if that's a valid index, in other words, if it's greater than or equal to 0, right, then I can go left. Right? Now, how do I go left? Right? So, or how do I solve the question, is the board solvable if I move left? Right? Well, you just call your isSolvable method, right? Because that solves that board if you move to a given the current location. Right? So you just change your current location to index minus value, right? And try to solve the board. Right? Notice that the board that gets passed to the next version of the method has a -1 on it. Right? So the next version of the method that gets called knows that there's a square that's been stepped on. Right? And that will eventually return true or false. Right? And we'll assign that value to when left. Right? Now, you can also go right. Right? So if you move right, can I move right? So if you move right, then your new location is just index plus value. Right? So if that's a valid index, if it's less than the size of the board, right, then try to move by going right. Sorry, try to win by going right. Right? So call is solvable. Right? Change your current location to the move to the right and pass in the board. Right? And remember, the board has a -1 on it to indicate that the current square has already been stepped on. Right? So now I've solved the problem of going left and right. Right? If either one of those is true, the board is solvable. Right? So if either when left or when right is true, right, then the answer is true. Right? If they're both false, the answer is false. Right? Before you return, though, you have to remember to undo what you did. Right? So I have to change the board at that index back to its original value. Right? Otherwise, the caller gets a modified board, which they probably don't want. Right? So there are your recursive cases. Now, what about the base cases? So when you write a base case for a method and it returns a Boolean value, right? It's almost certainly the case, well, it is certainly the case, that you have to have two base cases. Right? The reason you need two base cases is because you need to be able to return true from the method, and you need to be able to return false. Right? So, what are your base cases? Well, if you land on a square whose value is -1, that indicates that you're in a cycle. Right? And so the board is not solvable with that current move. Right? So you can return false. So there's your false base case. Now what about your true base case? So we know we're done if we reach the last square. Right? And so that's your true base case. Right? And there are your two base cases, right? Which are easy to code. Right? If you land on a square, right, and its value is less than 0, right, you're in a cycle. So we can return false. Right? This solution doesn't work. Right? If you end up on the last square of the board, so that has index size -1, then you've solved the board. Right? You return true. Right? And then you just stick in the recursive cases from the previous slides. Right? And I claim that that produces a correct solution. Right, any questions so far about using recursion or sublist? No? All right. Moving right along. Now I want to write a method that moves the smallest element in a list to the front of the list, and I want to do this recursively using recursion. Right, so it's easy to find the smallest element in a list, right? You just use a loop. It's easy to move it to the front if you found it, right? You just swap the first and the smallest element. Right? But how do you do it recursively? Right? So to solve it recursively, again, it's always useful to draw out a problem. Right? So I've got some list of random values, right? So the values 0 through 9, they're shuffled into some random order. Right? I'm going to ignore the first element of the list for the time being. Right? Instead, I want to look at the rest of the list, right? And I want to move the smallest element in that list to the front of that list. Right? So I don't care how you do this, right? We don't care how the recursive method does this. All that we care about is that the recursive method is going to move the smallest element to the front of the list. Right? So the 0 comes to the front, and we don't care what the rest of the values are. Right? Okay. Now I've got an 8 and a 0, right? The original 8, and I've got the smallest element in the rest of the list. Right? How do I move the smallest element to the front now that I've reached this step? Well, I just compare the 8 and the 0. Right? If that 0 is smaller than the 8, then I just switch the 0 and the 8. Right? If it's not smaller than the 8, then the 8 must be the smallest element in the list. Right? Because I've moved the smallest element in the rest of the list up into the second position. Right? So how do you code this up? Well, you literally just code up this picture. Right? So start with a base case. Right? I want to move the smallest element to the front of the list. Right? So if the list has size 0, there's no smallest element. So I guess we're done. Right? If the list has size 1, the smallest element is at the front of the list because there's only one element in the list. So we're done. Right? So if your size of your list is less than 2, there's nothing to do. The smallest element's already at the front of the list. Right? Now, the first step in our recursive method was move the smallest element in the rest of the list to the front of the sublist. Right? So if you remember that min to front moves the smallest element in T to the front of T, then you can just recursively call the method, right? Passing in the rest of the list. Right? So the rest of the list is just the sublist starting at index 1. Right? So in other words, T sublist 1T size is that list in blue. Right? I can move the smallest element of that list to the front just by calling the method recursively. Right? So I call min to front recursively, and that moves the smallest element to the front of the list. Right? Now I just have to do the last step. I compare the first and the second element in the list T. Right? So the first element, T get 0. Second element, T get 1. Compare the second to the first. Right? If the second is smaller than the first, then I switch them. Right? So T set 0 to second and T set 1 to first. Right? Just swap the first and second elements, and you're done. And believe it or not, right, that actually moves the smallest element in the list to the front of the list. Does that look weird to anybody? Yes.
Yeah, it looks weird to me.
Yeah, it's weird, right? It's bizarre.
If you move this sort dot into front like after those other
Yeah, then it doesn't work.
it's so
It doesn't work.
Oh, it doesn't?
No, it has to be there. It has to be there. It's bizarre, but it works. Right? So if you draw out the picture, so it's tedious, but if you draw out the picture, you can convince yourself that this does in fact work. Right? So for example, you start with a smaller list, right? So let's say a list of size 5 or something like that, or 4, right? And just follow the method recursively through and see what it does to the actual list, right? And you'll see that it does in fact move the smallest element to the front of the list. Right? This one's probably a bit unusual because the recursive call is in the middle of the method, right? Normally when students see recursion for the first time, the recursive call is normally at the end. But here, it's way up at the front, which is a bit funny. Right? So you recursively do something, and then you solve the rest of the problem after doing the recursion. All right, so what happens if you repeat this process? Right? So I move the smallest element to the front of the list. Right? So the 0 comes to the front. Right? And now, I call min to front on the rest of the list. Right? So if I do that, the 1 comes to the front. To the second place, right? It moves to the front of the blue list, right? And now you keep on going, right? So now I've got the rest of the list. So what if I call min to front on that, right? So now the 2 comes to the front of that list, right? And now I keep on going, right? So call min to front on the rest of the list, and now the 3 goes to the front of that list, right? So now you've got 3 here. Notice what's happening over here, right? We're sorting the entire list. Right? So by the time you get to the end of the list, right, I've got the 8 and the 9. Move the smallest to the front. That's the 8. Right? And now I'm just left with the 9. Right? If I call min to front on the list of size 1, we're done. Right? So nothing happens. Right? And when all of that happens, right, when that whole process happens, you end up with a sorted list. Right? And that's the selection sort algorithm, which you may have seen. I don't know if you've seen it or not. Right? But selection sort repeatedly finds the smallest element in the list and moves it up towards the front of the list. Right? Normally when you're taught selection sort, if you're taught selection sort, you're taught to do it iteratively, right? Because it's relatively easy to do with a loop. Right? But you can do it with recursion as well, right? As long as you have min to front. Right? There's selection sort. Right? If your list is bigger than size 1, right, then you might have to sort the list. Right? So how do you sort it? Well, I move the smallest element in the list to the front, and then I selection sort the rest of the list. Right? And so there's selection sort in 3 lines, right? Assuming you already have min to front implemented. Right? Strange, but true. This does in fact work. Right? And again, so this one's a little easier to understand. Right? If you just take for granted that min to front really does move the smallest element to the front of the list, right? And then looking at the pictures, you can convince yourself that that does in fact do the correct thing, right? Now, the recursive call moves the smallest element in the rest of the list to the front, right? And that keeps on going until you end up with a list of size 1, or with a list of size 1. Okay, do I want to do this? How much complexity analysis did you guys do? Some? Lots? Oh, sorry, question.
I just have a question.
Yeah.
Could you re-explain selection sort? I don't really understand it.
Okay, sure. So first of all, you have to take for granted that min to front moves the smallest element in the list T to the front of the list T, right? Okay. So let's go back to the picture here. Right. So if I start out with the list up here, right? After calling min to front, the 0 is at the front of the list, right? I don't care what the rest of the list looks like, but I know that the 0 is at the front of that list, right? Okay, so the smallest element's now at the front of the list T, right? I now need to sort the remainder of the list, right? So how do I sort the remainder of the list? Well, selection sort sorts a list, or at least we're assuming it sorts a list, right? So I just have to call selection sort, passing in the rest of the list, right? Sublist 1 comma t, t dot size gives you the rest of the list of t, right? And then you can selection sort that, right? So what does that do? It moves the smallest element to the front of that sublist, right? And then so on and so on and so on until you get to the end of the list. All right, so you've done a little bit of complexity analysis, right? So you know about big O of n, big O n squared, and stuff like that. Did they actually teach you how to count the number of elements in a function, the number of operations in a function, and then so you end up with what's called a, what do you normally call it? I forget, a timing function. Did they tell you how to do that? Yeah.
It was like in one of our slides.
In one slide.
They never really did.
In one slide, that's awesome. All right, great. So did they do complexity analysis of recursive algorithms?
Yeah, I think that's what it was. I don't
Of a recursive algorithm, but they didn't do it for a regular algorithm?
It was like probably 10 slides. I don't think any kid in the course would understand.
Awesome. That's fantastic. All right, what am I going to do here then? All right, so let's try to selection sort. What do I want to do? What time is it? Okay, so I'm going to stop there then. And in the next, so I'm going to insert a deck of slides where I actually teach you how to find, how to compute, or how to count the number of operations in a method, and then how to actually find the complexity of a recursive method. And hopefully, after this set of slides, after the next set of slides, you'll understand how to do complexity analysis. Right. So we'll stop for now. If you're in the lab, I'll see you in the lab for a little while. Otherwise, I'll see you next week.